Hello, am I audible? Okay. Okay, just let's wait for uh, few more minutes. Okay, 1 2 more minutes, and after that we'll start. Okay, is that cool with everyone?
Yeah, sure.
Okay.
Hello, good evening, everyone. I am Ajit Kumar, your host for the MLT series, proudly presented by Saranda House. In this series, we will truly explore and delve into the complete 12-week curriculum of MLT from our course. To guide us through this series, we are honored to have our esteemed mentor, Mr. Kshitij Pandey, who brings a wealth of expertise and insights to the session. And Kshitij is a TA for statistics too, and the lead teaching assistant for the minor in AI program at IIT Roper. On the behalf of Saranda House, let us extend a warm welcome to Mr. Kshitij Pandey. With that, I now hand over the session to him. Thank you. Okay, Kshitij.
Yeah. Thank you for the introduction. Yeah. So hi everyone. So in this session, what we'll do. So basically, in this series, what's our motive? Our motive is to help you guys in the MLT course. Okay. And now, in this week, in this session, what's our goal? So here, let me share my screen for a second. Wait a second. Yeah, just a second. Let me share my screen. Yeah. Okay, I hope my screen is visible. Yeah, is it visible now? Okay, unfortunately, let me try again to share just a single tab. Unfortunately, I'm not. Oh, yeah, no, now I'm getting the option. Okay, yeah. So, I mean, obviously, I have told you guys again once that in the series we will be covering MLT. Okay, and we'll try to explore a few more things apart from course. Okay, Yeah, so about the session, so each week we'll have two sessions. Okay, the first one will be a summary of week, and the second one will be more inclined towards problem solving and exploring something extra. Okay, so yeah, and for today's session, as you can see on the screen, what's our goal? Yeah, so first of all, we'll start with motivation of machine learning. Okay, we'll explore what is machine learning. Okay, we'll explore what is AI, what is ML, and what is DL. Then we'll explore types of machine learning, and then we'll jump into representation learning, the PCA. Okay, so is that clear to you all? Anything you guys want to ask before we start?
So what if I am doing MLF along with it MLT?
Okay. Yeah, it will be little difficult for you, but it's not impossible. Okay. There are a lot of people who have done this before. Okay. No need to worry. Whatever we have as prerequisite, it will be covered in the session. Okay. Whenever required.
Okay, sir.
Okay.
Sir, this session is for foundation level student.
No, this is not for foundation level student. This is for diploma students who have MLT this term.
Okay, sir. Thank you.
Okay. Yeah. So let's start. Yes, anyone?
No, sorry to disturb. May I know the duration of the today's lecture?
Yeah, most probably from 4 to 6.
Oh,
Okay,
okay.
it may extend.
Okay, thank you.
Okay, yeah. So let's start. Okay, so first of all, I mean, the course is machine learning techniques, right? So what is exactly machine learning? Okay, I mean, as you can see, the definition here, machine learning is the study of computer understanding and
Sir, are you audible?
Actually, you are not audible right now.
computer, and the computer gives us the output. Okay, let me see the chat. Is everything fine?
So now it's fine.
Okay, okay. Yeah, okay. And feel free to unmute in between, okay? You are welcome to interrupt.
Excuse me,
Yeah,
sir.
yes.
Sir, it is streaming online or not on YouTube or something where?
Well, I'm not aware about that, but the recording will be provided to you guys, okay? And I don't think it's getting streamed anywhere.
Okay, sir.
Yeah. Okay. So let's start this session. Yeah. So the first thing is, what is machine learning? Okay. So as you can see the definition here, machine learning is field of computer science that uses statistical techniques to give computer the ability to learn from data. And very important thing here is that without being explicitly programmed. Okay, so the first question is, okay, we understand what is learning from data a little bit, but what is this explicitly programmed? Okay, so explicit programming involves writing code for each specific scenario. Okay, but in the machine learning we don't do that. Okay, so uh, what do we do in traditional programming? We have data, okay, and we have logic. I mean the program, okay. Whatever we want as our output, according to that we write logic, that is we write program, we feed it to the computer and we get the output. Whereas in machine learning what we do, we have data and the output. Okay, basically here we are talking about label data, you can say. Okay, and when we feed it to the computer, uh, what happens, computer gives us the logic. Okay, it learns the logic basically. Okay, it learns the logic and gives you the desired output. Okay, it, by learning the logic we mean that it learns the uh, underlying relationship between your input and output. Okay, so this was a little about machine learning. So any problem here? Anyone? Yeah, am I
No,
going
sir.
too fast, too slow?
It's fine.
Okay, so let's continue our discussion. Yeah, so this was about machine learning. Now, I mean, you may have heard obviously, if you are in data science degree, so you have heard of ML, AI, and DL. Okay, deep learning, machine learning, and artificial intelligence. Okay, so let's talk about these terms a little. Okay, what they actually mean. So first of all, let's talk about AI. Okay, so as written over here, AI is a field focused on giving intelligence to machine. So I mean, we always have this curiosity of giving I mean, if you have watched a lot of movies, we always had this idea of giving machines, robots, in human like intelligence. Okay, in simple words, we want to make machine mimic human intelligence of reasoning, problem solving, pattern recognition, okay, and all that. And when we talk about human intelligence, it involves a lot of things, okay, like pattern recognition, creativity, emotional intelligence. But the AI systems we build are mostly on pattern recognition only. And why is that? Because it's very difficult to, I mean, do we really understand how emotions are developed in us? Do we have an equation for sadness? No, right? It's very complex. Okay, even we don't understand how our brain works. Okay, so the most AI systems we build are on pattern recognition only. Okay, okay, is that clear? So what is AI? AI is nothing but field that focuses on giving machine human-like intelligence. Okay, and as we have discussed, human intelligence include a lot of things like pattern recognition, creativity, and emotional intelligence. But the AI systems we build are mostly on pattern recognition. Okay, yeah. So any doubt here in this part?
No, sir.
No, sir.
Okay. Hmm. Now, let's talk a little about history, right? So, in the period 1950 to 1980s, symbolic AI was dominating the field. Okay, but what is symbolic AI first of all? Okay, symbolic AI is nothing but approach to artificial intelligence that uses symbols and rules to represent knowledge and solve problems. Okay, I mean, that was a complex definition, but think of it as teaching a computer to reason and make decision uh, like humans. Okay, so here in symbolic AI, we have two important things. Okay, two important terms: symbols and rules. Okay, so what are the symbols here? Okay, so these can be words, simple words, numbers. Okay, like car, red, fast. Okay, and based on these symbols we have relationship. Okay, that are called rules. Okay, so rules are nothing but logical statement that describe relationship between symbols. Okay, so here we have written that if a car is red, it might be fast. Okay, so we have symbols. You can think as of now, just think of it as words, numbers. Okay, and rules describing a relationship between different words and different numbers. Okay, now yeah, so now what happens with help of symbols and rules? Okay, so the computer uses these symbols and rules to store knowledge. Okay, it represents facts about the real world. Okay, like all cats are mammals. Okay, simple facts like these. Okay, and it may develop based on these knowledge. it may develop logic, okay, of drawing conclusion, like if Tom is a cat, then Tom is a mammal, okay. Simple things, okay. For example, imagine teaching a robot how to identify animals, okay, like dog, cats, okay. So in this case, these symbols we will have will be words related to dogs, cats, their qualities, and so on, okay. So here we have written that symbols we have like dog, cat, has fur, barks, meows, okay. And the rules that we have uh, can be like this, okay. So if it barks, it's a dog. If it meows, it's a cat. Simple, okay. Just like you teach a 5-year old, like not even a 5-year old, a toddler, right? Okay. So these are the rules, okay. And the robot uses these rules to figure out what it is looking at, okay. Is there any problem here? Is everything clear so far?
Clear, sir.
Okay. So now, okay, so in short, what we are doing here, in short, we are building knowledge systems, okay. We are collecting knowledge, and we are writing if else condition for all the scenarios, okay. So our system can deal with them, okay. So just look at all the statements we have written. All of these are if else statements, right? Okay. Like here, if Tom is cat, then Tom is mammal, okay. If it barks, it's a dog. If it meows, it's a cat, okay. So basically, one word conclusion for symbolic AI is that it is we are basically building knowledge systems based on if and if else conditions, okay. And based on this knowledge system, your AI will take decisions, okay. As simple as that. So whenever somebody uh, asks you about symbolic AI, the first thing that should click in your mind is that it uses if else conditions. Yeah, is that clear? Okay. Now, so in this era, so symbolic AI gave rise to two things. Okay, expert systems and game AI. So, what are expert systems? Okay, so look at the diagram. So, what basically we do in expert systems, we have human expert. Okay, let's say if we are building expert system for chess or Chinese game Go, we'll have a expert uh, at chess or Go. Okay, we will extract all the knowledge from the expert, human expert, and based on that, we will build knowledge base. Okay, and knowledge base, and we will have rules similar to what we have discussed above. Okay. And now, based on these rules, your AI will take decisions in game. Okay, as simple as that. Okay, so example for expert system can be like lung cancer detection system. Okay, and game AI you guys already know. Okay, so yeah, so this was it about symbolic AI. But I mean, as you can see, there are a lot of limitations, right? Our rules are limited, okay. Just look at the rules what we have written. It's like teaching a children something, okay. So what are the limitations of symbolic AI? Okay, so I mean, it won't be able to understand messy real world problems, right? Okay, like actually, I mean, even when I was writing this, I mean, I was, I mean, it's difficult to understand how can you just identify whether it's a cat or dog based on these simple rules. Okay, maybe you can train a dog to meow. Okay, yeah, that was just a joke. Yeah. Okay, so you can, I mean, it's very obvious what can be the limitations of symbolic AI. Okay. Yeah, and symbolic AI won't be able to learn new rules. Okay, so I mean, just think of expert system. Okay, let's say, okay, we have a warehouse which has all the possible chess moves for all possible scenarios. Okay, so I mean, if we have so rich knowledge, why can't our system learn or develop new things from this knowledge base? Okay, so that's one limitation. That's another limitation of symbolic AI. Okay, so yeah, now is symbolic AI clear? Hello, is symbolic AI clear and its limitations?
Yes, sir.
Yeah.
Yes, please.
So and now all this gave rise to machine learning. Okay, and what is machine learning? Simply, in simple words, it is learning from data. Okay, and we have already discussed what is machine learning. Okay, so the next thing is we'll talk about deep learning a little. Okay, so what is deep learning? It's not like deep learning is completely different thing or something. Okay, so you can think of deep learning algorithms as a class of algorithm that are inspired from our biology, basically our brain. And why we say that? Because the core unit of deep learning, that is the perceptron that we will cover in this course, is based on neuron. I mean, it's not completely based on neuron. You can say it is inspired from neuron. Okay, and we will talk about this in week 9. Okay, when after studying MLT. Okay, this may be not very clear at the moment, but this will get clear after we study perceptron. Okay. Hmm. So for now, we can think of deep learning as okay. Uh, they are a class of a class of algorithms, okay, that are inspired from neurons. Okay, they are inspired from brain. Okay, so basically you can think of, okay, it is a technique to solve more complex problems. Okay, machine learning problems. Okay, and what's the benefit of deep learning? Okay, the main benefit is this. Look at this diagram. Okay, yeah, so let's say we are working on a classification problem. Okay, we give image. Okay, and we have to detect it, is there a car in image or not? Okay, so in machine learning, what we have to do, from the image we have to extract features. Okay, so basically when we talk about images, if you guys know that images are nothing but they are three matrix stacked over each other. Okay, so all the images are coming from RGB, right? Red, blue, green. Okay, so any image can be represented using three matrices. Okay. So I'll give you, let me share my screen and I'll show you one thing. Or yeah, just a second, I'll paste one image. Yeah, just a second. Let's look at this image. Okay. Yeah. So this is image. Okay, this is your image here, and this is a black and white image. Okay, so this can be represented using a matrix. Okay, and when we talk about colored images, it will be represented using three matrices. Okay, one for red channel, one for blue channel, and one for green channel. Okay, so we have, okay, now we have three matrix, okay, representing a image. So what we can do, we can stack all the rows of all the three matrices and make vector. Okay, and that vector will be our input for the algorithm. Okay, so in this course, all the, I mean, whenever we talk about machine learning, the input is vector, that we already know, right? So what we have to do in addition here, from image we have to extract matrix, three matrices, and from there we have to make a vector. Okay, and only after that we can work on our machine learning algorithm. Okay, so this part is called feature extraction. Okay, but in deep learning, what's the benefit? That you don't have to do feature extraction. Okay, you don't have to do that. The model itself will take care of that. Okay, so simply you will feed it, you will feed the model images, and it will do the feature extraction part itself. Okay, so this is one benefit of deep learning. Okay, so so it automatically, as it's as written, it automatically attracts features from raw data. Okay, and eliminates the need for manual feature engineering. Okay, this we just discussed. Okay, yeah. So if deep learning is this good, why to use machine learning? That's the question. Huh. So for this we have a graph here. Okay, so uh, I mean, deep learning has recently it's recently booming. Okay, from past. I mean, you can say. I mean, I don't know exactly. Maybe from 2010s. And why is that? Because we have a lot of data. Not just data. We have labeled data as well with us. Okay, and we have good hardware as well. Okay, like GPU, TPUs. So when why not to use deep learning only? Okay, so the thing is that your deep learning model is data hungry. It need data a lot of data it needs. Okay, so whenever you have less, you don't have a lot of data, it is better to use machine learning algorithms over deep learning algorithms. Okay, and in the graph here, as you can see, so what happens with machine learning? Its performance increases as the amount of data increases. Okay, and after certain time it plateaus. Okay, it saturates. So no matter how much data you give after this point, the performance will not improve. Okay, whereas with deep learning, what happens? The performance increases with increase in amount of data. Okay, and here you can think of this as elbow point. Okay, before this elbow point, machine learning, as you can see, is performing better than deep learning model. Okay, so is that clear?
Yes, sir.
Yeah. So now is it
But
clear?
as per your graph, sorry, uh, but as per your graph, the amount of data seems to be same, correct? But is it a representation issue, or because when you discussed, it said for deep learning, you need the quantum of data will be very high, which even I was having in my mind. But in this graph, we can see like the amount of
Yeah.
data seems to be okay, correct? For both the things.
Okay, so you can train your model with less data, but the performance will not be that good. To get a good performance from deep learning model, you need lots of data.
Okay.
Yeah. So now tell me guys, is it clear what is AI, what is machine learning, what is deep learning, why deep learning is good, but why still we use machine learning? Why not to just use deep learning? So are all these questions answered?
I have a doubt here. Uh, am I audible, by the way?
Yes, yes, you are.
Yeah, I was just thinking that, as you said, in deep learning we can do all the problems if we have the enough data. So I was just thinking if all the tasks that we do using deep learning can that also be done using machine learning.
Okay, but the issue is performance. Okay, that's
Yeah,
the core issue. Okay,
yeah,
I mean, you can a train model on any problem. Okay, machine learning model on any problem, but the performance may not be that good. Okay.
okay. So it's like we can do tasks, it's not very efficient. So my main the thinking point was like if we can create chatbots and others using machine learning only. So
I mean, they require a lot of data, right? If you, I
mhm,
mean, I saw this graph for the amount of data needed. It's enormous how much data is needed for creating chatbots. You know?
got it. Okay.
Yeah. Okay. Yeah, anyone else? Anything? Okay, so let's move. So now let's conclude. Okay, let's conclude on our discussion about uh, AI, ML, and D. Okay, so what is AI? So AI is nothing but giving. Wait a second. Giving human-like intelligence to computer. And what is machine learning? It is one efficient system for making AI. You can say, okay, for making AI. Okay, and what is deep learning? Deep learning is a subset of machine learning which is used on complex problems. Okay, so I'll just write used for complex problems. Okay. Yeah. So now, so generally, whenever we talk about difference between machine learning, deep learning, AI, this is the first thing we see. Okay. So is this Venn diagram making sense now to you guys?
Yes, please.
Yes, sir.
Okay. Yeah. Okay. So now this means you guys have understood what is machine learning, what is AI, what is deep learning, and how they are connected to each other. Okay. Now, the next thing we have to discuss is types of machine learning. Okay, and this is based on amount of supervision needed. Okay, yeah. So we can broadly classify machine learning into four categories. Okay, one is supervised learning, second is unsupervised learning, then comes semi-supervised, and after that, reinforcement learning. Okay, and about about supervised, we can again divide supervised learning problems into two categories. One is regression problem and other is classification problem. Okay, and in unsupervised techniques we have in unsupervised problems we have clustering, dimensionality reduction, anomaly detection, and association. Okay, so now let's discuss a little about these things. Okay, we'll just discuss a little about these things because the entire course is based on this. Okay, yeah. So throughout the in this course, we will just study this. Okay, yeah. Now let's talk about supervised learning. What is supervised learning? Okay, okay, okay. So talking about supervised learning. Okay. So what is supervised learning? Okay, whenever we are given data set for any problem and the data has is labeled data, you can say. Okay, it has input as well as output. So for example, let's say let's have a representation of data. Okay, so the data is represented like set of input output labels. Okay, so the input is vector. Okay, all the inputs are vector, and output may be vector, maybe a scalar. Okay, just a second. Make it like this. Okay, so maybe all these input are vectors we have generated from images. Okay, so let's say we are working on classification problem, simple dog cat classification problem, and all these xi's are nothing but vector we have extracted from images, and all these yi's are nothing but they are the label. Okay, is it a dog image or cat image? Okay, so for that, we can use 0, 1 for representation. Okay. So whenever we are given data set which has input and output, okay, and our job is to understand the mathematical relationship between input and output to predict output for unseen data. Okay, so this is your supervised learning. Okay, why is this is called supervised? Because we are given supervision. Okay, we are already told, okay, this is the image and the image is of a cat. This is the image and the image is of a dog. Okay, that's why this is called supervised learning. Okay, so the key point in supervised learning is that the data set is such that we are given input output values, and our job is to learn the underlying mathematical relationship between input output and predict output for unseen data. Okay, so is machine learning clear? What is the idea of machine learning?
Yeah.
Okay.
Learning from data.
Yes, come again, please.
Learning from data
Yeah,
and
correct.
predict.
Yeah, learning from labeled data, that would be better. Yeah. Now, in machine learning, in supervised learning, we have two problems. Okay, one is regression problem. Regression problem. Okay, and the other is classification problem. Okay, so why do we have these? On what basis do we have this division? So the division of supervised learning is based on the type of output, the type of label. Okay, it is. So basically, when we talk about data, there are going back to stats one. There are two types of classification for data, right? One is numerical, and the other one is categorical. Okay, so let's say let's take a simple example of predicting house price based on features like a number of bedrooms, number of washrooms, how far is the nearest school, how far is the nearest hospital, and so on. Okay, these are the features, and these features can be represented in vector form, and the output here that will be a continuous number, right? It won't be categorical. Whereas when we talk about the classification of dog cat image, it is a classification problem. The output is your categorical data. Okay, so let's say we can represent dog as 1, cat as 0. Okay, so based on the output, we have divided supervised learning into regression. And what is regression? When output is numeric.
Or continuous, we can say.
Yeah, that's correct. So numerical and continuous, correct? Okay. And I mean, basically you can say the output belongs to RD. Okay, it may be a vector or a scalar. Okay, whereas for classification problem, the output is categorical in nature. Like 0 for cat, 1 for dog. Okay. Yeah. So is the idea of supervised learning clear? And the idea of regression problem and classification problem? Yeah. Any doubt here? Okay. Okay. Now let's move to unsupervised learning. Okay. Yeah. So what's the difference in unsupervised learning? Okay. Here we don't have supervision. And what do we mean by that? The output is not given to us. We are only given data, not the label, you can say. Okay. For example, we are just given images. Okay. The image are of cat and dog, but we are not told what is a cat, what is a dog. Okay. So the main difference is that in unsupervised learning, we don't have y's. Okay. We only have xi's. Okay. And in supervised learning, first thing we have is clustering. Okay. So here for unsupervised learning, I'll simply write is not given. And when we are talking about clustering, okay, let's talk about clustering now. Just a second. So let's take a simple example. Okay. Let's say we have a race. Okay. And people from different countries are participating in the race, and we have recorded the amount of time taken by players to finish the race. Okay. So the time taken, that will be on x-axis, right? We can represent that. I mean, we can plot time taken on x-axis, correct? Now let's say some people took less time. Okay, whereas other people took little more time. Okay, and few people took a lot of time to finish the race. Okay, so now as you can see here, okay, so these are forming clusters, we can say. Okay, so I mean it from our understanding, we can say, okay, obviously people from few countries, because of the biology and environment, okay, because of evolution, they have a fast twitch fiber, okay, fast twitch tissue. Okay, I'm not very good at biology. Yeah, so they have a lot of fast twitch tissues. Okay, and you can say, for example, people from Kenya, okay, they are very good at running, you can say. Okay, so that's why it is forming clusters, because we have in our race people from different countries. Okay, So this may represent one country, this may represent other, and this may represent another country. Okay. So this is the use of clustering. We can divide the population on clusters. Okay, and the one other example we can take is that, let's say we have data for IQ and CGPA of students. Okay, and when we plot this data, we are getting clusters. Okay, this is one cluster, this is another cluster. Okay, so maybe this cluster is for smart student but not hard working student. These are hard-working students. Okay, and where this can be useful. Okay, so companies may want to classify or categorize, okay, their customers based on their buying patterns. Okay, let's say someone is buying expensive but less items, whereas someone else is buying not expensive but a lot of items. Okay, so company wants to class company wants to have divide the customers in different clusters. Okay, so that they can recommend them different product. Okay, so this is the other use of clustering. Okay, so basically we don't have labels. Okay, we just have data, and data can form clusters. Okay, so these are in 1D and 2D, right? So we can plot them on our own and find different clusters. But when we have a lot of features, when the data is present in higher dimension, even there it form clusters. Okay, but we cannot plot them. Okay, so there are techniques like KNN that solves the problem. Okay, basically KNN measures the Euclidean distance. Okay, it works on Euclidean distance. Okay, yeah, so that's the idea of clustering. Is that clear? Okay. Yeah, we'll talk in depth about these things in this course. Okay. The next thing is dimensionality reduction, the first part of our course. Yeah. So what dimensionality reduction does? Okay. So let's say we have the problem of predicting house price. Okay. So let's say we have features like number of number of bedrooms. Okay, and number of washrooms. Okay, and we have a lot of other features as well. So what PCA does, it reduces the dimension of data. Okay, so what it will do, okay, it will combine these two and make a feature like square feet. Okay, square feet area. Basically, if we have if number of bedrooms are increasing, number of washrooms are increasing, basically the square foot area of the house is increasing. Okay, you can say roughly. Okay, so this is the one use of dimensionality reduction. Okay, so basically it does feature extraction, you can say. And the
Does this square foot area already exist in the data set, or is it something that's like new that is being
shown?
No, it does not. Okay, this is a toy example. So basically, the idea of dimensionality reduction is that it will form new features from existing features. Okay, it will combine few features and make new features. Okay, it will not be something like this is a toy example, so that's why I have written here square foot area. But maybe the combined features is like number of bedrooms plus number of washrooms divided by root 2. It's something like that. Okay, this is a toy example, so we have written that. Feature reduction, yeah, you can say that it is feature extraction and reducing the feature, correct. So the name itself tells us that it is we are reducing the dimension. Okay, and the other use of dimensionality reduction is that visualization. Okay, so this is one use, and the other use is visualization. Let's say your data is present in like 4 R700. Okay, but obviously you can't visualize it. So what you'll do, you will reduce dimensionality reduction techniques, and you will bring down your data in 3D and visualize it. Okay, so I'll show you guys one example of it. So the other thing is visualization. Yeah, let me share other screen. Let me just a second. Let me stop sharing and reshare my screen. Yeah. Is my screen visible?
Yes, sir.
Okay. Yeah. So this is MNIST data. Basically, this is data of digits. Okay, photos of digits. Okay, as you can see here. So as we have just discussed, that image, a black and white image can be represented using a matrix, whereas a colored image is represented using three matrices stacked on each other. Okay, so now here we have 28. This image is of 28 by 28 pixels. Okay, and that is represented by uh, this matrix here. So for making vector, what we'll do, we will stack all the rows on top of each other. Not row, my bad, columns. You will stack all the columns on top of each other, and that will give you a vector in dimension 784. Okay, so our data set here is in dimension 784. Okay, so with dimensionality reduction techniques, what we can do, we can reduce the dimension to 3 and visualize it. Okay, I'll just show you just a second. Yeah, look at this. Yeah, so this is the MNIST data in 3D. Okay, you have reduced your dimension from 780 something to 3. Okay, and as you can see here, so here you have yes, someone is asking something. Yes, feel free to unmute.
Yes, hello, sir. So now you reduce this dimension from 780 to 3. So what all does the algorithm choose the features like the column names, like the features?
What it does, it we'll discuss this in this video on in this lecture, that it combines a few features, okay, and make a new feature, as we just discussed. For a toy example, it may combine a number of bedroom, number of washroom, two features, and make area in square foot, a new feature. Okay, so it is doing that.
But how will we interpret it? Like, what's the use for us? Like, for example, if we take height and weight, it's a two-dimensional data set, and if we reduce it to one dimension, what do we get actually? Like, how will we interpret it?
Okay, that we'll discuss. Okay, in the in this session only. Okay, in the later part of the session.
Okay.
Okay, yeah, yeah. So as you can see, this is the visualization, and one thing about it, let us zoom in a little. Yeah, okay, not this much. Okay, yeah. So as you can see, this these green dots represent 3. Okay, so 3 which are 3 points, I mean the points which represent 3 which are close to each other, as you can see in the image, they have similar handwriting. Okay, whereas let's take a look at this point. Okay, see the handwriting, whereas when you look at a point representing 3 which is far from that point, the handwriting is different. Okay, but when you look at the points which are close to each other, the handwriting is similar. Okay, so it is capturing the reduced data is also capturing the essence of the true data. I mean, by true data I mean the original data. So it is basically capturing the same information but in 3D. Okay, so is this clear? Do you have do you have idea of dimensionality reduction, what it tries to do? Yeah, so I'll share this link with you guys. Do explore this. Yeah. Okay, now let's move to the next part, that is anomaly detection. Just a second. Yeah. Now, when talking about anomaly detection, okay, I hope my screen is visible, is it? So yeah, now we'll talk about anomaly detection. Okay. So from the word itself, anomaly, okay, uh, here we want to identify the outliers. Okay. Yeah, this is not in our course. Okay, yeah, but just to know the term, okay, we are discussing it here. So I have one image. Yeah, here it is. Yeah. So like you have normal data like this. Okay, so this is your normal data, and uh, these are the new points. Okay, so what basically we want to capture here. Okay, we have our new data. Okay, and whenever there is new data, okay, we want to identify, is it anomaly or not, is it outlier or not. That's the basic idea of anomaly detection. So it can be used in classification problem as well as regression problem. Like let's say for stock price you have fluctuation like this. Okay, but let's say suddenly you have spike like this, so this is anomaly. Okay, so this we want to identify. Okay, so I mean, we don't have to talk a lot in depth about this. Okay, maybe in the future we can discuss this. Okay, yeah, I just wanted to introduce the term, that's why brought this. Okay, and the next thing is the next thing is association. Yeah,
So,
so
sir, anomaly, we can simply say abnormality in the data. Or
correct, absolutely correct.
okay, sir.
Do you mean the outliers or the data pattern itself is anomaly? It's
We
only
want
out.
to identify outliers for new data, for unseen data. We want to identify, is it outlier or not.
Okay.
Yeah.
So which algorithm is used for this?
I mean, I mean, even I haven't touched this a lot. Okay, I mean, even I have high level. I mean, even I just have this much understanding. Okay, we can discuss the algorithm later. Okay. Yeah. Is that clear? Yeah, this is not very important here.
Okay, sir.
Yeah. If you guys want, we can discuss this in more detail in next class. Okay. The next thing here we have is association. Okay. Yeah. So what's the idea of association? Okay. So if you have paid attention in grocery stores, few items are yes. This is okay. This is not. This is okay. So these sessions are basically initiative from house. Okay, we have. We will just cover the MLT course. Okay. Yeah, this is not workshop or anything from the course team of MLT. Okay. Yeah, this is from Saranda House only.
Okay, okay.
Yeah. Now, talking about association. Okay. So, what's the idea of association? Yeah. So we have all been in shopping malls. Okay, grocery stores. So, few items are kept together. Okay. So the idea is that we want to understand the in this example we want to understand the buying patterns of customers. So what we'll do, we will go through the bills, okay, and we will identify what items have correlation. Okay, so maybe you go through bills and you identify, okay, whenever customer buys milk, he tends to buy eggs also. Okay, so you will keep those two together. Okay, and there was a study on this. Okay, that there is association in beer and diapers. Okay, this is a wild association, yeah, but using machine learning we were able to detect the association between that. There is an association between beer and diapers, so it is beneficial. It would benefit the business if we keep beer and diapers together. Yeah, yes. Yes, Raj Rishi. uh, you have raised your hand. Okay. Yeah, please feel free to unmute.
Hello, can you hear me?
Yes, I can hear you.
Yeah. So here in association, is it similar to finding correlation between variables?
Yeah, you can say that, but we don't have. I mean, we are not here just discussing the depths of the association. We are just introducing the term. That's it. Okay. So you don't have to think a lot about it. Okay, we can discuss this in future sessions. Okay, it's not even in our course. Okay. Yeah. So no need to worry. If you guys want a separate discussion on association and anomaly detection, we'll definitely have it in future. Okay. But for now, we are just introducing the terms. That's it. Yeah. And so yeah. So this is the idea of association. Okay. So I'll share one that paper with you guys. Okay. That identified that there is a uh, relation between beer and diaper. Okay. Yeah. Just a second. Let me share. Yeah, I'm sharing the link of article. Yeah, you can go through it if you are curious. Yeah. Correct, Ram. Yes. Yeah. So this is it about the supervised learning. Okay. Okay. Yeah. So the idea here is to just introduce you guys to the terms used. Okay, that's it. Just to give you a little idea about what is regression classification, clustering, dimensionality reduction, and all these. Okay, yeah. So is there any problem? Is there any doubt? Anyone? Okay.
You will be sharing these notes?
Yeah, sure.
Thank you. Where? Because I'm not part of this house.
We will share the notes in the mail. So that was we will have a different again we have a session, so we will share all the resources to you. So kindly be patient and focused on the session. Okay, and you can if
Sure.
you have general doubts, you can ask in the chat box.
Yeah. So basically, in our course, we will study about supervised learning, and in unsupervised learning, we'll study about clustering, dimensionality reduction. Okay. Now, just to introduce you all to the term supervised, semi-supervised learning and reinforcement learning. Okay. So what happens in semi-supervised learning? So the thing is that labeling data is very expensive. Okay, so that requires human effort to label data. When we talk about MS data, all these label data, they required human effort. That's why they are very expensive. So idea here is that we have some labeled data and some unlabeled data, and we work on that. Okay, whereas the idea of reinforcement learning is that you don't have data, you have agent. Okay, so I'll share one image with you guys here. This image. Yeah. So in reinforcement learning, we have agent. Okay, so the model is agent, and based on model's own experience, it learns. Like you have agent, and it will have set of rules. Okay, to move or something. If it moves in direction of fire, we'll deduct the points. Okay, if it moves in some other direction, we will reward it. Okay, so it learns from its own experience. That's the idea of reinforcement learning. Okay, like for games, the AI agent for games are from reinforcement learning. Okay, and how do they become expert in games? They play it million times. Okay, for a million hours or something like that, and that's how they become expert. Okay, yeah. So this was about reinforcement learning.
So it is giving me feeling of sequential learning.
Yeah, because yeah, correct.
So
Yeah.
is they are same?
I mean, you can say they have intersection or something. Okay, we don't have to discuss about this at the moment. Okay, yeah, together we'll develop the maturity for understanding these all these terms. Okay, throughout the course. Yeah.
Yeah, under sequential learning, this reinforcement learning is coming into picture, and sequential is every time it understands something and it improvises. Even
Yes.
sir
Okay.
Arun sir has said in the I think week 1.2 he has spoken about it, I suppose.
Yeah. Yes. Thank you for adding. Yeah. Okay. So maybe that answers the question, right?
Yeah.
Okay. Yeah. Thank you. I mean, okay. Sorry, but the name is not visible here. The username is first of all your name. No. Thank you. Yeah. Okay. Now let's. All this was motivation. Okay. To the MLT course. Okay. Now let's start with the actual course. Okay. Yeah. Okay. Okay. So just a second. So in week 1, we will start our journey of unsupervised learning. Okay. Yeah. First of all, one quick question from all of you. How many of you have seen the lectures? Please raise hand. Okay. All those who have seen lectures, please raise your hand.
Week 1 lectures, no?
Yes, yes. Let's see what's the proportion. Yeah. Okay, so far 10 people have raised hands. Okay. Yeah, I request those who have seen the lecture, please raise hand. Okay, so looks like okay.
One more criteria you need to check, like all the 80 people in the class, are they registered for MLT this time? That
Okay,
question also we need to take. That is very important.
okay, okay,
Or you
okay. I
can add
thought
who has not registered. That will be better. That
okay,
number you
sure.
need to minus. Yeah.
Yeah, yeah, okay. People are. I mean, I was not expecting that people without MLT course this term will register will join the session. Okay, I people are very curious. So, okay, good. Okay, yeah. You guys can lower your hand now. Yeah, yeah, that poll will take now. How many of you have not taken MLT course this term? Let's see how many of you are super curious people. Okay, wow, you guys are very curious. Okay. Oh, one is oh, the number is literally large. It's greater than the number of people who have seen the lectures. Okay, I appreciate you guys joined. Oh, amazing. Okay, yeah. Thanks for the participation in poll. You guys can lower your hand now. Okay. Okay, now let's start the actual content. Okay. So, yeah. So, week 1. So, here we will discuss about unsupervised learning. Okay. Even in that, we'll discuss about representation learning, dimensionality reduction technique, which is principal component analysis. Okay. Yeah. Unsupervised learning. Okay, so what's our goal of this representation learning? Okay, so given the data, we want to understand something useful. We want to extract something useful out of the data, and also you can say we want to compress the data. We want to bring it to the lower dimension. Okay, so obviously the data, whatever data we have, data it is data points are vectors. Okay, they are vectors in R3, sorry, in RD. Okay, yes. So this is the setup. All the data we have is in vector, and in representation learning, our goal is to gain to understand something useful from the data, and also to you can say compress the data. Okay. So now the input we have. So input we have is a collection of vectors. Okay, yeah, this is our data set. Just a second. Okay, and all these xi belong to RD. Okay, so let's say for example we have data. Okay, and these are the vectors. Let's say Okay, these are the data points. Now let's ask us ourselves a question: how many numbers are required here to store the data? As there are 4 vectors and the data is in R2, we need 8 numbers to store data. 8 numbers are needed to store the data. Okay, but here what we want to compress the data. Okay, we don't want to store data in 8 numbers. Okay, we want to store it in less memory. Okay, so as you can see, all the data points here, the observation here is that all of them lie on a straight. Okay, so now you can say, okay, whenever your data is such that it lies on a straight line, okay, it lies on a straight line. Okay, so what you can do, you can have 2 things. Okay, you will compress the data using 2 things. One is representative. Okay, so what is a representative? Okay, it is nothing but a vector lying in the same line on the same line. Okay, that's your representative. Okay, so representative you have. Okay, so let's say this anything can be representative. Okay, yeah, this is your representative. And what else you have? You have coefficients. Okay, so depending on the representative, you will have coefficients. Okay, so what you want to do? So you want to multiply the coefficient with the vector and come back to the original vector. Okay, so to come back to the original vector, -7, -14, the coefficient here is -7. Similarly, 0.5, 0. 2.5, 0.5, and 0. So these are the coefficient. So yeah, and one important thing is that zero vector can't be representative. Okay. Okay, I mean that's obvious, right? Because no matter what coefficient you take, you won't be able to go back to the original vector. Okay, yes. So here, is this doing any benefit? Okay, yes, obviously, because now how many numbers are required here? 1, 2, 3, 4, 5, 6. Okay, so 6 number here are required now. But I mean, this is a toy example, right? You don't. The real world data is not this simple. Okay, so what will happen? The data you may have will not fall on a straight line. Okay, and that will happen in 99.99% cases. Okay, yeah. So one thing here, yeah, I may want to add is that here, I mean, in general, the number of the numbers required to store the data will be d times n, where d is the dimension in which the data is living, and n is the number of points. Okay, and in this way, when your data is in a is just on a straight line, okay, the compressed representation will need d plus n points. Yeah, Now let's get back. Let's go back to the real world data, right? So the real world data is not this simple. Okay. So what you will have points which are not on the plane. Okay. Sorry, my bad. Which are not on the line. Okay. So let me just. Okay. Or what I'll do, I'll just make a graph. Okay, and we'll just copy that graph. So this may take few minutes. Not a few minutes, yeah, few seconds. Let's make a clean graph.
Sir, I
Yeah.
have a doubt.
Yes.
How you got 6 there?
Yeah.
Coefficients.
So he 6 here represents the number of okay, the number required. Let's say, for example, let's say to store this data, to store the original data, the memory units required are 8. I mean, one unit for each number. Okay, so that's why for this 8 uh, units of memory is required to store this data. Whereas when you just want to store these numbers, okay, your representation and your coefficient, how many unit of memory will be required? 1, 2, 3, 4, 5, 6.
Okay, got it.
Sir, how we get representative?
Yeah, representative. You can choose any vector lying on this line can be representative. Okay, but except zero vector.
Oh, any number. It may not be in the data set. It must be or it may not be.
Yes. Yeah, it may not be in the data set. This vector is not in the data set, but this is our represent. We have chosen this as representative, and according to the representative, you will have your coefficient. Okay, and the coefficients are such that you get back the original data you have. Okay, so now we yes.
Is there any relationship between representative and coefficients and data?
Could you please come again?
Is there any relationship between representative, coefficient, and data?
Relationship, yes, there is relationship, right? Because on multiplying the coefficient on multiplying the representative with coefficient, you get back the original data. So when you multiply -7 with this vector, you get the original vector -7 -40 and so on.
For properly, you have to choose like that.
Yes, whatever representative you choose, according to that you have to choose your coefficients, such so that you generate your original data from there.
Thank you.
Okay. Now let's talk about real world data. Okay. So in almost all the cases, what will happen? The data you have will not be this simple. It will not lie on a number line. Okay. So let me just give me a minute. I'll just draw a simple graph. A neat. Wait a second. Yeah, just give me a minute. I'll draw a neat graph. Okay. Yeah, thanks for the patience. Yeah. So now, whatever the real world data will not lie on a straight line. Okay, so let's say this is your line. Okay, now, and the data points are like this. Okay, so let's say just for illustration, we'll only take one data point outside the line. Okay, and all rest of the points are here. Okay, yes. So now what we can do? So one possible solution is that, okay, so the data is in R2. So the basis vector, from the basis vector, we can, from the linear combination of basis vector, we can reach any vector. Okay, so so one approach is that you will have a representative, and what are the representative? You will have two vectors as representative. Okay, the two vectors will be orthogonal. Okay, whatever vectors you take, they will be orthogonal, or any two vectors. Sorry, any two vectors in R2. Okay, yes. From the linear combination of the two, we can span the entire space. So let's say the representative we take is 1 0 and 0 1. So from linear combination of these two vectors, we can reach any point, right? So this is our representative, and according to this we will have coefficient. Okay, so now you'll have coefficients. Okay, I'm not writing the coefficients. Yeah, so you'll have some coefficients. Okay, let me write the other coefficients. Yeah, it would be better in understanding why we will not use this method. Yeah, so these are the coefficients. Yeah. So is this helping us? One question, right? So how many unit of memory is required here? Okay, so two vectors, they are in R2. Okay, so 4 unit of memory for this, and for each pair of coefficient, 2 units. So 2 unit, 2 unit, 4, 6, 8, 10. Okay, 10, 12, 14. 40 units are required here. Okay, this is not helping us, right? For the original data, we just had 8 unit of memory, but here this is taking way more units of memory. Okay, yes, so this method is not helping us. Okay, so what can we do? Okay, so now what we'll do, okay, so the idea is that we will have a proxy for data points which are not on the line. Okay, and what is a proxy? Proxy is nothing but a good representative of that point. Okay, so what is a good representative of that point? Okay, that we want to find now. Okay, yeah, and one important thing is that the good representative we are talking about will lie on the line. So now what we want to find, we want to find a proxy for data point on a proxy for the data point on the line. Okay, yes. So now we want to find the point which captures most of the same information as the original point. Okay, or you can say we want to find a point which is similar to our original point on the line. Okay, so for that, what we'll do? Okay, so now this is the big question. Okay, so now okay, so we can have multiple points, right? We can take this point, this point, this point. Now what point to take? That's the question. Okay, so whatever point we take, okay, so closer the point is to the point, similar the point is from the original point. Okay, that's the main thing. Okay, so now let's say let me frame this in a clean way. Okay, yeah, so just a second. Okay, leave this. Just give me a second, I'll just clean things up a little. Yeah, so now what we will have here, Okay, just let me make one more graph. Okay. Yeah. Please be a little patient. Okay. Yes. Yeah, thanks for being patient. Now, so now we are finding the proxy for the point which is not on the line. Okay. So, and let's say our representative is this point. Sorry, no, this vector is our representative. It is vector W, which is W1, W2. Okay. And now the point we are talking about is this. This is x1, x2. Okay. So we want to find proxy. Okay. So we can take multiple points. Okay. I mean, this is proxy we are taking. This is the proxy we are taking. This is the proxy we are taking. So the question is, what is which point we have to take as proxy? So the point closest to this point on the line will be the proxy, will be the good proxy. Okay. So now let's say, okay, so let's draw the perpendicular here. Okay, so the perpendicular will be the, I mean, we already know that the point perpendicular, I mean, this point here will be the closest point to it. Okay, yeah. So now we want to find this point. Okay, and this right here is the error. I mean, this is the, you can say this is the information we are losing, right? So this is the original point. If we are replacing this point with this point, this much is the information we are losing. Okay. The original point, let me draw as vector. Yeah, this is the original vector. Okay, yeah. I'm using here a point and vectors interchangeably. Okay, so don't get confused. So this is your original. This is W is the representative. This is the vector, the point we are talking about. Okay, and right here will be your proxy. This is your proxy. Okay, so what this proxy will be some scalar times the W vector, right? The representative. Okay. So now we want to find such a vector on the line such that the error, so the you can say the distance from the original point and the point on the line is minimum, and being more technical, the error is minimum. Okay, so now what we want to find, we want to find C such that, I mean, C will give you the vector, right? The proxy vector. Okay, so we want to find C which minimizes this length right here, which I have represented using green bracket here. Okay, yeah. So yeah, and we talk about norm square, that is length square. Okay. Okay, and what is this error vector? Yes, so here is x1, x2, okay, minus c times w1 minus c times w2. Yes. So we want to minimize this length. We want to find c such that this length is minimum. Okay. Now let's do that. Okay. So this is the vector, and how we will find the norm square? We already know. So the norm here will be x1 minus c times w1 square plus x2 minus c times w2 norm square. Okay, so this is nothing but, I mean, we are using Euclidean distance here. Okay, now we want to find optimal c. So for that, what we will do, we will differentiate this with respect to c and equate it to 0. Okay, so now let's differentiate this. So we'll differentiate this. So do you guys want me to differentiate, or do I write the final result? Yeah, so this is, yeah, we are differentiating this with respect to C and equating it to 0. So now this is simple differentiation, right? So this will be equal to minus 2 times W1, x1 minus C times W1, minus 2 times W2, x2 minus C times W2, and this is equal to 0. Okay, so we will cancel 2. Okay, we'll cancel 2 and we'll simplify. So we will have E times W1 square minus x times W1 plus C times W2 square minus x times x2 times W2, okay, multiplied with W2, okay. Yeah, and this is equal to 0. So what we'll do now, we'll have terms involving C on this side and move everything else on the other side. So what we'll have, and we'll say take C common as well. So we'll have W1 square plus W2 square equal to x1 W1 plus x2 W2. Okay, now what is your optimal C? So from here, your optimal C is nothing but x1 W1 plus x2 W2 divided by, just a second, yeah, divided by W1 square plus W2 square. So this is your optimal W. Okay, and quick observation in here is that this right here, the numerator is nothing but dot product of vector representing the point, that is x vector, and the representative vector W vector. And in the denominator, we have the norm square of W vector. Okay, so one important thing here is that we can always pick W such that the norm is equal to 1. Okay, so I'll just write it here. Note, we can such that the length is equal to 1. So now, so the numerator is equal to 1 now in that case. So what is the C star? It is nothing but X transpose W multiplied with so this is the value of C. Okay, this is the value of C. And now what is the proxy? The proxy is W times this, right? This is the C we wanted to find. So the so the proxy now is X transpose W, X transpose W times the W representative vector. So this is the proxy right here. Okay, yeah, any problem here, anyone? Anyone, any problem here?
No.
Okay, now let's continue. Okay, so now what we have understood right here. Okay, so for the vector is not on the line, we will find proxy. Okay, and basically these are nothing but projection of this vector on the line. Okay, yeah, so we'll project the vector on the line. Okay, so now the the problem has changed a little, right? So we are given points and we want to find a line such that the error is minimum. Okay, and let's write it properly. Okay, yeah. So now we are given data set, right? Okay. We are given data set belonging to RD. Okay, and the error. Okay, so what line, there is a line we want to find now. Okay, so such that the error given by the line and data points. Okay, so we will have data points, and let's say we have a ideal line. Okay, so for this ideal line, the error will be minimum compared to all the lines. Okay, yeah. So how do we measure the error? Error is nothing but summation of all the uh, length square. Okay, for all. So this we have discussed for a single point. There will be a lot of points like this. Okay, so the error we will calculate for all the points, and the summation will be our actual error for the entire data set. Okay. Okay, so summation for I from 1 to n, error. Yeah. So, and what is the error actually for points? The error is nothing but the length square of a vector, this vector right here, this vector. Okay. So what is this vector? This vector is nothing but this is equal to the original point minus the c times, I mean the c here is xi transpose w. So the proxy, so basically error minus the proxy vector. Okay. Sorry, the original vector minus the proxy vector. This will give you error vector. Okay, and we have this as our error. Okay, so we will calculate this for all the points. Okay, the error. Yeah, and now this is just simplify this. Okay, doing little algebra here. 1 to n. So we want to find norm square, right? Length square. Okay, yeah. So now to further simplify this, we will just simply write. So we all know that norm, let's say norm square of x is equal to x transpose x. So we are using that simple. So we'll use a little algebra here. Yeah. So yeah, it would be. I mean, we can take sum of the error as well as the average error. Okay. So when we are, let's say we are taking average error. Okay. Yeah. I from 1 to n, and the norm of this. Okay, so norm of xi minus xi transpose w to w. Okay, yeah. So the formula we'll use now, simple. Yeah, transpose of this multiplied with itself. So xi minus xi transpose w into w. Now we can further simplify it, right? Yes. So I mean, now what you can do for simplification, take this transpose inside. Okay, so what will happen? You will have transpose of xi, then transpose of this entire thing. This right here is a scalar, so we will have transpose of w only. Okay, and now do multiply it. Okay, yeah. So the result I can write, or do you guys want me to show the simplification? Yeah,
Please,
guys.
please show the simplification by.
Okay, sure. Yeah, guys. The thing is, I'm writing over there, right? I can't see how many of you have raised hand. So directly unmute yourself. Okay, if you have anything to ask. Is there anything anyone wants to ask? Hello.
Is it mean
I see
square
few
error?
of you. Yes, this is mean square. Yes. Pratik, is there anything you want to ask or add? Pratik, you have raised your hand. Okay, no problem. I think it's an accident. Yeah. So yeah, I'll just show you guys the simplification. Okay. Yeah. Okay, so for simplification, what we'll do, we'll multiply one by one. So just a second. Yeah. So first of all, bring the transpose inside. Okay. So what you'll have, xi transpose minus scalar. So you'll this will have no effect, times w transpose. Okay. And here you have xi minus xi transpose w into w. Now just multiply these. Okay, so first of all multiply xi transpose with both the terms. So yeah, so this will be xi transpose xi, then multiply xi transpose with this term. So this will be minus, and the scalar we have, so we'll write it first. So xi transpose w xi transpose w. Okay. Yeah, so this is the same thing, right? So this is also a scalar. And now multiply the second term of first bracket with the xi. So here what we'll have same thing. Okay, we'll get the same thing. Wait a second, here you'll have a plus. Yeah, here you'll have the same thing but negative. Okay, so these two will get cancelled. Okay, and now the last term, here what we have, here we have square of this term. Okay, so xi transpose w, square of this scalar, and this w transpose w, this will give you norm square of w, and we know that this is equal to 1. Okay, so now we are left with this 1 by n summation I from 1 to n xi transpose xi plus square of this scalar. Okay, yes, so we are left with this. Wait a second. Is there any problem? Yeah, just a second. Just let me go through it once. Yeah, wait a second. Yeah, this is one mistake. Yeah, so here this term will be, yeah, so this term will be negative. Here this term will be negative because we are multiplying this with this. Okay. Yeah, so now this term will get cancelled. Okay, so just a second, small error here. Yeah, just let me fix this. Xi transpose w. Yes. So now these two will get cancelled. Okay. So we'll have this. Okay. Now this is your error we want to minimize. Okay. So minimizing. Okay. So let me frame this again. Minimize for w, where norm of w norm square of w is equal to 1. And what is your function of w? It is 1 by and we are, wait a second, we are minimizing this entire thing, right? And here this is not in our hand. Okay, this comes from data, and only this thing is in our hand. Okay, so minimizing this is same as, so if we are minimizing this whole thing, in what case this will be minimum? When this term is maximum, right? When this term is maximum, in that case this entire thing will be minimum, correct? Is that clear?
Yes.
Okay, yeah, so basically this minimizing this is same as maximizing this term. Okay, nothing, we are just writing that now. Okay, so summation I from 1 to n, so minimizing this. Okay, so this is same as maximizing for w, where norm square of w is equal to 1. Okay, and what is the objective function? This is the objective function. Okay, yes, now we can further simplify it. Okay, so we'll just bring it in a clean fashion. We'll just write it in a better way. Okay, nothing, just algebra here. So yeah, so this can be written as square is, right? We have square, so we'll just write the same term, multiply.
Did you miss one term, sir?
Yes.
Yeah, xi transpose xi becomes that minimum line before that line.
Where
Yeah,
what portion?
after strikeout, we are getting 1 by n into summation I equal to 1 to n xi transpose xi minus
This
what?
term, this term.
Yeah. That
Okay,
becomes.
so the thing is, the problem is to minimize this. Okay.
That is okay.
And this is not in our hand. This is what? This is data, correct? This is coming from data, correct?
Okay.
The only thing in our hand is this. Okay. Correct?
Okay. Yeah, we have to
because
maximize the if you maximize the means for error will become minimum, the accuracy will become high.
Yes, correct. So this problem is minimizing this is same as maximizing this. Okay, so the W we get is same.
Before that line, I am asking minimum over W, that G of 0, G of W equal to 1 by n. How you are writing this line?
Okay, yes. So basically, we are minimizing this. So what we are saying, okay, this is not in our hand because this comes from data. Okay, so this is a constant. We can ignore this. Okay,
Yeah.
so now we are saying minimizing this thing is same as minimizing this. And you can see here, this is negative here.
Okay, minimizing means, okay.
I mean,
If we maximize, then only it will be, that term is maximizing, then only it becomes okay. What do you come to say? I don't understand. Oh, negative value minimizing means.
Yeah, if you minimize the negative value, basically you are pushing it towards. I mean, this number is getting large, right? This is becoming large. Larger the value of this
Larger,
number.
yeah. That's what I'm
Yes,
asking. Yeah. Okay.
smaller this quantity.
Yeah. Okay. Understood.
Yeah.
Understood.
Okay. Yeah. So now just do a little more simplification, and what you will do now, okay, just expand this, okay. So xi transpose w, xi transpose w. Okay. So what we can do now? So here, I mean, the net resulted outcome that will have dimension of row of this xi transpose and column of this w. Okay, that will be the size of resulted. Okay, so now just little manipulation here, and you can write this as summation I from 1 to n transpose, and here you have xi transpose. Okay, and this will not change the result. Okay, because the the size, I mean the shape of this resultant will be same as shape of this resultant. Okay, that's fine. You can verify that. Okay. Wait a second. I made a small mistake here. Yeah. This will be, this right here will be W transpose Xi. Yes. So we are not doing anything, right? I mean, we literally just said, okay, multiply these two. There is no,
This associative?
correct. Yes, correct. So, I mean, we are just saying, okay, multiply these two things first of all, okay? Yeah. So why we did this? Because this right here is nothing but this Xi into Xi transpose is nothing but your covariance matrix. Okay, so if you have already done the prerequisite MLF, you may have came across this covariance matrix. What is covariance matrix? This is 1 by n times summation I from 1 to n Xi into Xi transpose. This is your covariance matrix and it is represented by C. Okay, and it is D across D matrix. Okay, so for those who don't know covariance matrix, let me give you guys a little introduction for covariance matrix. Okay, yeah, just a second. I have an image. Just a second. Yeah, this is how you calculate your covariance matrix. Yes. So what is covariance matrix actually? So whatever data you have, I mean, the covariance matrix will measure the covariance between different pairs of vectors, right? So here, this will, the first term will measure covariance of x with itself, which is variance of x. The next will measure covariance of x with y, then x with z. Then the second row, we are measuring covariance of y with x, okay, which is same as this, and covariance of y with itself, which is variance of y, and the final thing here is covariance of y with z. Okay, so the matrix here will be same thing. Okay, so here uh, the element in the matrix on, let's say, some position ij, okay, that will measure the covariance of x with sorry, ith vector with jth vector. Yeah, yes, Pratik. Hello, Pratik, you have raised your hand. Yeah. Any doubt here in covariance matrix? Any doubt so far here?
No, sir. No, sir.
Okay. Yes. So now let's continue our discussion. Okay. Yeah. Okay. So now we have made it clear, right? So from a very cloudy problem, we have come to optimization problem now. Okay, we are finding W such that this is maximum. Okay. Okay. So now what's next? What are we achieving here? Okay? That's the question. Okay. Yeah. So I'll just rewrite this in a better form. Yeah. So this is nothing but this is equivalently problem of maximizing for W such that norm square of W square is equal to 1, and the objective function is W transpose CW. Okay, where C is the covariance matrix. Okay, yes. So now let's look what is happening here. Okay, so geometrically, let's say let me just copy this. Okay, yeah. So geometrically, Yeah, so let's say this is 3D, right? This is 3D plane. Okay, so this is 3D world, and here we have data points. Okay, but the data points actually, I mean, they live in 3D, but they actually lie in a 2D surface, on a 2D surface. There is a 2D surface, and all the vectors lie here. Okay, all the vectors are living here. Okay. Okay, let me choose a different color. So all the vectors lie here. Okay, these are all our vectors. So what you will do, we will find proxies for these vectors on a line. We want to find a optimal line, right? Such that this value is maximum or the error is minimum for simplicity. Okay, we want to find a line. Okay, let's say this is the line. The line is this. Okay, this is the line with minimum error. Okay, this is the optimal line, the best fit line. Okay, now what's happening? So we are leaving these vectors. Okay, we are projecting all the vectors on this line. Okay, so we project vectors. So what are we losing? So we are saying this is error. This right here is error, but actually what is happening, this is the true point. We are using this point as a proxy. Okay, there is actually a loss of information because this point here contains the actual information. Okay, but we are using this, so there is a loss of information in this as well. Okay, so how can we capture the lost information now? Okay, so if you look carefully, all these vectors, all these error vectors, all these error vectors right here are parallel or anti-parallel to each other. Okay, and if you shift them, they lie on a straight line. Okay, that means they have some information in them. This is not error, this is actually information. For our optimization to frame our optimization, we said it is error, but actually it contains some information that we are losing out when we are replacing the vector with a proxy vector. Okay, now we want to capture this. Okay, so how can we capture this now? That's the question. Yeah, any problem here? Any difficulty you have? Anything you want to ask? Anyone?
Please can you repeat? Please can you repeat?
Yes. So what are we doing? Okay, we have an actual data point. This is your actual data point. Okay, but in place of this, you are storing a proxy for this point, which is a best representative of this point, but still we are losing information. Okay, I mean, let's say for example, we have this the vector represents number of bedroom and bathrooms. Okay, we have projected it. Okay, so this point right here uh, will be different from this point, right? And the difference, this is the difference, right? This is the difference. This has information. Okay, you cannot say this point exactly represents this point of actual data set. Okay, there is information we are losing. Okay, is that clear? Is it, first of all, tell me, is it clear that we are losing information when we are storing a proxy in place of original vector? Is that clear?
Yes.
So now we are saying, okay, we are losing information. Okay, now we want to capture that information we are losing. This is the question right here. Okay, is it clear? What's the thing we want to capture now? the information lost when we are storing proxy vectors in place of original vectors. Is it clear to you all?
Yes.
Okay. Yeah. So all these vectors, they are parallel or anti-parallel to each other. All these error vector. Okay. So obviously any vector we can shift. Okay. Okay. We all know that any vector we can shift to origin. Okay. So when you shift all these vectors to origin, they line up. They will line up. Okay. So now we want to capture this information as well. Okay. So how we will do that? That's the next question. Okay. So what we will do? Okay. Let's see the possible algorithm. Let's phrase the entire problem again. Okay. Yeah. So now what we had? Okay, we had xi's belonging to. Wait a second. Yeah. So we had xi's belonging to RD. We wanted to find the optimal W. Okay. Optimal W such that the error is minimum, and that was this. Okay, X transpose. Yeah, yes, we wanted to find the optimal W such that the error for all the points is minimum. Okay, and this was the C for the proxy vector. Okay, and this is the proxy vector now here. Okay, so your error, what is your error now? Your error or residue is xi minus xi transpose W into W. Okay, and we are saying this error is actually not error. We said this is error because we were solving optimization problem. Okay, so actually this contains information. This stores information. Okay, so this might have information. Okay, and based on this, what's the possible algorithm for the problem we are dealing with? Okay. Okay, so here we have input. Okay, our input is nothing but xi's. Okay, and xi belong to RT. Okay, and now we want to find the best line. Okay, so find best line. By that we mean find the optimal W. Okay, and after that what we said, okay, we have done this, but now we have information in the error vectors as well. Okay, so what we'll do now, we will treat the error vectors as our data now. Okay, and we will repeat this same thing on the error vectors. Okay, so what you will do now, so our now at this stage, what's our data? We replace, replace xi with xi minus xi transpose W to W. Okay, so these now are our points now. Okay, so what you will do, you will again do the same thing for these points as well. You will find the best W. Okay, and then again you will get error vectors. Okay, and then again you will repeat this step. Okay, repeat to find W2, W3 and so on. Okay, so repeat this, repeat to find W2. Okay, yeah, so this is possible algorithm. Yeah, and yeah, there's one problem, that is if our data is not centered. Okay, yeah, so those who have already done PCA in MLF, they may be familiar with this step. So if data is not centered, what we will do, so what's the problem with not data which is not centered? Let's see. Just a second. Yeah, clear. So let's say these are our data points. Okay, these are our data points. So actually, our algorithm, what it is doing, it is finding line passing through the origin, the best line passing through the origin, such that the error is minimal. But the problem here is that now here the x-axis has less error compared to, let's say, the line, this line that you will get from the algorithm. Okay. Okay, so that's the problem. Okay, the error here is less compared to error we are getting when projecting on here. Okay, so that's why we want to center our data. By that, what we mean, we want to shift the entire data to center. And how we will do that? We have a step here. So here we have a step. Okay, to center our data. So you have mean. So from all the vectors, you will find a mean. Okay. Okay, this is your mean. And now you will, so the data points you will replace with xi minus mean. So you will subtract mean from all the data. Okay, and that will be your centered data for all I. Okay, now this will be centered. Okay, it will be somewhere here, and this will be the line, a better line, okay, compared to any other line. Okay, yeah, so this was the issue. Yeah, and now what questions we have in mind? Okay, how many times do we have to repeat? Okay, that's the question. Okay, we do have a lot of questions now. So one thing, let's talk about. So the line we get, okay, whatever line we get, basically, line form is formed because of the points, right? So whatever proxy point we get, okay, those the points we are getting on projecting are the points capturing the most information from the original data. Okay, you can say approximately, let's say these proxies, the proxy of this vector, we have find this proxy captures the it captures 80% of information stored in this vector, but we are losing out 20%. Okay, yeah, so now the error vector, we will line them up. Okay, so we now, after finding the first optimal line, we repeat the process for error vectors as well, okay, to find W2. Okay, is that clear? Any problem here so far? Any doubt?
No, what is the last statement you said? 80% we capture it and 20% we are losing, and after that you said something.
Yeah. So we are saying, okay, when we are storing proxy vectors in place of original vectors, what is happening? Okay, so we are losing out on some information. Okay, as we are choosing the best vector that represents this vector, that means that we are capturing 90%. Let's say I'm just giving random number. Let's say we are capturing 80% of information stored in this vector by this vector right here. Okay, because this is the best representation of this vector. on the line.
Yeah.
Okay, so that's why we are saying, okay, it will capture most of the information, you can say, of the original point. Okay, but we again want to capture the information we lose, the information we lose when we are using proxy in place of real data. Yeah. So for capturing proxy, what we are doing, anyone? For capturing the information in proxy, sorry, my bad. For capturing the information, we lose what we are doing. Anyone? Okay, so for capturing the information, what we will do, we will now the data points we have is of error vectors. Okay, now what we'll do, we'll have all the error vectors and we will find best line for the error vectors. Okay, so this gives you the second line. Okay, and that line will be perpendicular to this line. And why is that? Because as you can see here from this graph, just a second. Yeah, from this graph, all the error vectors are perpendicular to the line, right? Wait a second, what's happening? Let me fix this. Yeah. So all the error vectors we have are perpendicular to the best fit line. Okay, so obviously, I mean, you can move the vectors to origin. Okay, so all the vectors will be like this. So obviously, the best fit line will be in same direction, correct? And this direction is perpendicular to the best fit line. So our W2, let me show you here. Yeah, so this is your W1. So your W2 will be this vector or this vector. Okay, and let's see. Okay, let me draw one more thing. Yeah, so we are drawing the residue vectors. Okay, let's draw it here. Yeah, now talking about the residue vectors, these green vectors. So these vectors, you will shift all of them to origin. Sorry, just a second. Yeah. So all these will line up on a straight line. Okay, these are all the residue vectors. So now, I mean, this is the best fit line itself. Okay, this is the best fit line, and now there will be no error, right? There will be zero error, correct? Is that clear? Why there will be zero error now? Any doubt here? Are you guys able to understand? Hello?
No, the best fit line is there in that, falling in the first and the third coordinate. And what you are finding here after repeating the iterations of W1,
yeah.
W2, W3?
Yes. So now, now what we have done, we have first of all we are finding the best fit line for data points. Okay. Now you are looking at the error vectors because error vectors contain information. Okay. So now you are working as if your error vector is your new data set. Okay, and you are finding best fit line for the error vectors, for the error vectors. Okay, and that will be this. I mean, all the error vectors will be on a line because all of them are in same direction. By direction, I mean all of them are perpendicular to the original best fit line. Okay. So when you move all the vectors to origin, I mean, because all whatever algebra we do are on vectors starting from the origin, so we'll shift all of them. Okay, and you can also think of this as again centering the data. Okay, so now all of them will fall on a line, and the best fit line is this line itself. And now, as all of them are on a straight line, there is no error now. Correct? And why there is no error mathematically, if you see? So, what is the proxy? Look, proxy right here was nothing but dot product of the point with W vector and multiplied with the W vector. So when X vector and W vector, they are parallel or anti-parallel, the dot product is 0, right?
Yes.
Correct?
Yes.
Okay. Yeah. So that's why there is no error now. Okay. So this means you have captured more the information in the error now. Is that clear? So
yes.
yeah. So for data in 3D, first of all, we project all the data points on a best fit line. After that, we project all the now all the error vectors, they will line up. Okay, so automatically there is a best fit line for that as well. Okay, so to get zero residue error, how many iteration you have to do for 3D data? 2 iterations. Okay, first is for projecting the finding the best fit line for the data points. After that, finding the best fit line for the error points, for the error vectors. Okay, and after that, if you will project, there is zero error now, so you don't have to do the iteration anymore. But let's say for 5D data, we have to do this 4 times. So for 5D data, we will do this 4 times. So then the error will be on the 5th time, the error will be 0. Okay, so now, I mean, when we are talking about this, okay, these are the proxies. So now there is no error. Okay, so if you will again do this, the error is equal to 0. Okay, so for data in RD, the dth iteration of this possible algorithm, will give you 0 error. Okay. Is there any doubt? Is it clear? Okay. Yeah, so it's already 6:20. So we have a few things left. I mean, we have a lot of things left from week 1. Okay, we'll continue them in the next session. Okay, we'll inform you guys about the next session. Most probably we can have next session on Wednesday. Okay. Yeah.
So what do we have to do to get notifications?
Could you come again? Your voice was not clear.
What do we have to do to get the notifications for these lectures?
I mean, the house will drop you guys mail, okay, regarding that.
Geeta, we are from a different house. So Raja is from the same house and he has posted it and we are using it.
We will share the session information to the all students. So you will get a calendar invite. As today you got the calendar invite, right?
No, I
Have you got
Yes,
the
sir.
calendar?
Yes, sir. From the calendar only I came.
No, sir, we didn't get
So
calendar.
No,
okay,
we did
so
not.
I guess you are not subscribed to the student activities channel. Okay, fine. I will share the reminder as well as the next session information via mail to you guys. Okay, fine.
Yeah. So regarding continue. Abhishek.
So how many sessions did we miss so far? Is this the first one?
This is the first session. This is the first session, and we will have planned to cover this whole MLT series, means whole 12 weeks of the MLT course.
Okay.
Yeah. So most probably the next session will have on Wednesday. Okay, you can consider it locked. Okay, but if there is any change, we'll notify you. Okay. Yeah. And okay, thanks for joining the session, guys. Abhishek, now you can stop the recording. Okay.
And
Yeah.
thank you, Kshitij, for the sessions and the effort.
Yeah. Thank you, Abhishek, for.
By which
Yes.
subject you are taking mentorship and TA this time?
Yeah, this time I'm not. Yeah, could you stop the recording?